Okay, welcome back everybody. So today we're starting a new chapter in Physics 46. That is chapter 27 of the textbook. And the topic of this chapter is magnetism. Now, magnetism is also going to be covered in chapters that follow, 28 and 29. But this is really our introductory chapter to magnetism, where we lay the foundation. So the first topic in this lecture is just a really brief introduction to magnets and magnetic fields. We need to get a handle on these concepts before we start making any calculations or looking at equations. So let's do that introduction real quick. And so when we talk about the phenomenon of magnetism, this is something that has been known about for a very, very long time, because magnetism is something that just naturally occurs in the world. So, for instance, it's been noted that you can find certain types of rocks that if you put them together in a certain way, they attract, and if you put them next to each other in another way, they repel each other. So this idea of attraction and repulsion of these rocks was given the name magnetism. So what is a magnet fundamentally? What are the basic features of it? Well, all magnets have two poles, which basically tell you where the magnetic force is the strongest. Okay, so you're going to have the strongest magnetic effect right next to one of these poles. And any magnet whatsoever, if you allow it to rotate freely, so for instance, you could maybe take a magnet and suspend it from a string, well, one end of that magnet is always going to be pointing north. And the other end of that magnet is always going to be pointing south. So that's why we call these the north and the south poles of the magnet. Because if some magnet is free to rotate, it always likes to align itself so that one end is pointing north and the other end is pointing south. And this is how a compass works. This is basically the operating principle behind a compass, which is that the needle of a compass is a tiny little magnet which is free to rotate. And if we just put that compass on a table and just watch what happens to the needle, well, one end of that needle is going to point north, so that's the north pole of the magnet. The other is going to point south. That's the south pole of the magnet. Okay, and this is how you can tell which way north is. There's a lot more to say about that, because for some reason, the Earth itself kind of acts like a giant magnet to make this needle point in just the right way, so we'll get into that in a second. But before we do that, let's just take note of one basic fact about magnets, which is opposite magnetic poles attract and like magnetic poles repel. So for instance, if I take two magnets like this, each one is going to have a north pole and a south pole, and I put them together so that the north pole of one magnet is as close as possible to the south pole of the other, well, they're going to want to come together. They're going to attract each other. On the other hand, if I take two opposite poles and put them together, the magnets will repel. So if I have north-north or south-south like this, we're going to get repulsion. The force will be pointing outwards as opposed to inwards. So that's the idea. And actually, I thought I'd do a quick demo just to show this a little bit more clearly. So right here, I've got a compass, and the red needle of this compass is just telling me which way north is. So the red needle is pointing north towards Mount Baldy, more or less. And again, the reason it's lining up this way is the Earth itself has what we call the magnetic field, and the needle of this compass likes to align with that magnetic field. Now I'm going to take a really strong magnet, which has a much stronger magnetic field than the Earth could ever produce, and just put it next to the compass needle, and watch what happens. It looks like the needle is not really pointing north anymore. It's just sort of lining itself up with the magnet that I'm holding to it. Okay? So remember what I said a second ago. The red needle is the north pole of the magnet. The other side must be the south pole. And it looks like the south pole is attracted to the end that I'm holding near it. So I must be holding the north pole of this magnet really close to the needle to make this happen. But check this out. Watch when I flip the magnet I'm holding, so it's pointing the opposite end towards the needle, and now the north pole of that needle is attracted to my magnet. Okay? So again, this is just a basic demonstration of this idea of magnetic attraction and repulsion and how we can use that in a compass needle. And that takes us to the idea of a magnetic field. Okay? So we have this idea of an electric field that we've been developing for a really long time. And, well, what's a field in the first place? Well, a field is just a number that's associated with every point in space. Okay? And we have a vector field. That is a vector which is associated with every single number in place. Every single point in space, sorry. So when we have a magnetic field, this is an example of a vector field where at every single point in space, there is a vector telling us something about the magnetic field. Okay? So any vector has a magnitude and a direction. So let's try to understand what the direction of the magnetic field is telling us. And if we start with that, the direction of a magnetic field is just the direction that the north needle of a compass would point if you placed it at that location. Okay, so here I have a bar magnet, and what I want you to imagine is taking a compass and putting it right next to that bar magnet, and of course the needle of the compass is going to be affected by this, and it's going to point in a certain direction. Whichever direction this needle is pointing, that's the direction of my magnetic field. So if my magnetic field is pointing straight down this way, that means if I place a compass right there, the needle is going to point straight down. Okay, if I put a compass right here, and the needle is pointing kind of down and to the left, well, that's the direction of the magnetic field there. And one thing you should take note of from this picture is that my magnetic field lines, they go in a certain direction. If you start at the north pole of a magnet like this, the magnetic field lines will come out of that north pole, loop back around into the south pole, and then back to the north pole. So in other words, these magnetic field lines are kind of forming loops, which again, you can trace them starting at the north pole, all the way back around to the south pole, and then back to the north pole. Okay, so one thing I forgot to mention just a second ago was why is it that I'm using the variable B and the term B field as a shorthand for magnetic field? Well, it's basically a historical accident. Okay, so we are just from here on out going to use the variable B for magnetic field. So B field is the same thing as saying magnetic field, it's just a shorthand. Okay, so that's what the direction of a magnetic field is telling you. What about the magnitude? Well, okay, if we go back to this diagram here, we'll notice that in certain locations, the magnetic field lines are spaced very far apart, and in other locations, the magnetic field lines are bunched up much closer together. When they're further apart, that's telling us that the magnitude of the magnetic field is smaller, and when they're bunched up closer together, that's telling us that the magnetic field is stronger. And this is the same as what we saw for electric fields, if you recall. So when the electric field lines are really closely packed together, you have a really strong field. When they're really spread out, you have a weaker field. And once again, I'd like to show you a demo using the compass needle and the magnet, just to show you how you can sort of map out what the magnetic field from a magnet looks like using a compass. Okay, so this is the magnet, and if I put the compass, let's say right here, okay, it looks like the north pole, or the north needle of my compass is pointing right towards this red cap. Okay, and if I move it a little bit to the side, yeah, it's pointing right down towards that red cap. So that's telling me that at least here, the magnetic field is going straight down like this. But what happens if I sort of move the needle around? Okay, well now it looks like, oops. So yeah, these things do stick together. Now it looks like if I'm over here, my magnetic field is pointing straight up. And then if I bring it around even further, looks like I'm pointing straight down again. So I can actually sort of sketch that out. So what do we have? I have the magnetic field pointing straight down here, and then pointing straight up here, and then pointing straight down here. It looks like this is one of my magnetic field lines. Okay, so I could keep sort of moving the needle around the paper to see what the magnetic field looks like, but hopefully you get the idea of how that would work. All right, so we haven't yet really said anything about what causes a magnetic field. Okay, so why is it that there's a really strong magnetic field around this magnet that I'm holding, and why the Earth itself has a magnetic field? Where do magnetic fields come from in the first place? Well, that's actually a topic for the next chapter, which is 28. So I'm going to just really briefly say something about it here, and then chapter 28 is all about the origin or the causes of magnetic fields. So we'll get to that next. But if I could say it in a really brief way, every single magnetic field that you can think of is ultimately being produced by moving charges. So if you've got charges moving around in some way, you're going to have a magnetic field. And, well, charge moving around, that's just what we call an electrical current that we discussed in the last two chapters. Okay? And to get kind of a sense of this, let's take a look at this video where what's happening, we're connecting a battery to form a circuit, and once the experimenter puts this electrical lead up to the battery, some current is going to start flowing. And you notice that as soon as current starts flowing, the compass needle right underneath the wire starts getting deflected. So that's telling you that because there's current flowing in this wire, it's creating a magnetic field, and that can be detected by the compass needle. Okay? And in fact, every single magnetic field works this way. It's ultimately being created by moving charge. Okay? Now notice, as soon as we take the electrical lead away from the battery and then current stops flowing, the needle goes back to normal. So that's also telling us that if the charges aren't moving and they're just stationary, that doesn't create a magnetic field. Okay? So it's only moving charges that create a magnetic field. And so, in brief, what have we learned in many, many chapters of electricity and magnetism so far? Well, one thing we learned way back in chapter 21 is that a static charge that's not moving, that creates an E field. And then a moving charge, as we just found out, that creates a B field. Okay, so that's the origin of electric fields and magnetic fields. Okay, so the next thing we need to talk about is the Earth's magnetic field. So it's actually striking. The Earth's magnetic field is kind of complicated, but it really closely resembles the magnetic field of a giant bar magnet. Okay? So if you actually plot out the magnetic field lines of the Earth, it's as if there's just a giant bar magnet somewhere there in the center of the Earth. Okay, so on Earth, when we talk about the North Pole and the South Pole, this can get a little bit confusing because there's sort of two senses in which we can talk about the North Pole and the South Pole. Okay? Now, one way that we refer to the North Pole and the South Pole has to do with the way the Earth is rotating. Okay, so this line right here, this dashed line, is showing us Earth's axis of rotation. So this is the line that the Earth spins around as it rotates. Okay, so of course, if we go to the top of the Earth here, we could call that the North Pole, where our rotation axis comes out. Or down here, we could call this the South Pole, where our rotation axis comes out. But the magnetic field is actually not lined up with the rotation axis. Okay, it's actually a little bit offset. So in other words, if we think of the Earth as having a giant bar magnet inside of it, it's not actually going to be lined up with the rotation axis of the Earth. Okay? And to make things even more confusing and complicated, okay, remember how if you point a compass needle, if you take a compass and just see which way the needle is pointing, it's going to be pointing north? Well, the north needle of a compass isn't attracted to the north pole of a magnet, it's attracted to the south pole of the magnet. Right? So actually, what we think of as the North Pole is actually the magnetic South Pole. Because again, this north needle on a compass always is going to point towards the South Pole of a magnet. That's how magnetic attraction works. And so, I said they're offset, these two poles, the rotational pole and the magnetic pole. They're offset by about 900 kilometers. So unless you're actually really close to the North Pole or the South Pole, this doesn't really matter that much, right? Because when we're down here, a needle points north, it doesn't really matter that much whether we're talking about the North Pole or the South Pole. They're pretty close to each other. But let's say you're exploring in the Arctic and you're using a compass to show you which way you're going. Yeah, that's not going to be very useful actually. Because again, these are not perfectly lined up. And then you might wonder, I just said that it's electrical current that always produces a magnetic field. Anytime you have a magnetic field, you know there's some kind of electrical current that's causing it. So what kind of electrical current is there in the Earth? It's not like there's a giant circuit or some charge flowing through a wire inside of the Earth. Well, to understand what causes the Earth's magnetic field, we have to understand that the core of the Earth is basically molten liquid iron. And when you have a bunch of molten iron flowing around, essentially you have a whole bunch of current flowing in the core of the Earth. And that's the origin of Earth's magnetic field. Now, I've completely glossed over the details, and in fact, the exact mechanism for Earth's magnetic field is not fully understood. It's very complicated, and it's still an open question as to exactly how this molten iron in the core is producing the magnetic field, but that's roughly speaking how it works. Okay, now just to give you a quick sense as to how complicated the mechanism of the Earth's magnetic field actually is, it turns out the Earth's magnetic field actually just suddenly flips, reverses direction every couple 100,000 years. So in other words, this has happened many, many times throughout the history of the Earth, where what was once the South Pole just all of a sudden becomes the North Pole. Right? This is something that actually happens throughout Earth's history. Okay? All right, so again, that was just giving you a bunch of sort of different thoughts to think about. Now let's kind of hone in on something that we can work with, which is what kind of forces are felt when an object is inside of a magnetic field. Okay, so if I place some kind of object in a magnetic field, what kind of force is going to be exerted on it? And to start, I'm going to focus our attention on wires. So if I put a wire carrying an electrical current in a magnetic field, what kind of force is that wire going to feel? That's what I want to talk about right now. And actually, to understand anything about the force that a wire feels when it's in a magnetic field, we need to review cross products, because the entire math of this is given by cross products. Okay, so this should be a review, but let's go over it. Let's start by saying, let's let vector C be the cross product of vectors A and B. So in other words, we have the equation that says C is equal to A cross B. I want to know what C is given that I know A and B. Okay? So there are two things. When you do a cross product, you actually get out a vector. So the result of doing a cross product is another vector. So we need to know the magnitude of that vector C and the direction of that vector C. So let's start with the magnitude. Okay, the magnitude of a cross product is given by this. The magnitude of vector C is equal to the magnitude of vector A times the magnitude of vector B times sine of the angle between them. So in that sense, it looks a lot like a dot product, except instead of cosine, we have sine. And just to give you a sense, if this is vector A, this is vector B, both lying in the plane of the page, theta is the angle between them. Okay? All right, but unlike a dot product, there's another step to this, because we also need to know what the direction of our cross product is, because of course we're getting a vector out. So the direction of vector C is perpendicular to A and B. So whenever you take the cross product of two vectors, the resultant vector that you get is perpendicular to both of those. Okay? All right, so I look at my vectors here, A and B. They lie in the plane of this page. So it looks like if I want to be perpendicular to both of those, Well, my vector c has to point out this way, towards you guys. But actually, there's a problem. The other option is it can point in, okay, away from you guys. So we have two options, right? It's either pointing out of the page or into the page, given the way that it's set up here. And so we have to choose which one of those is correct, which is why we have the right-hand rule. Okay, the right-hand rule says, we're going to start by pointing the fingers of your right hand in the direction of the first vector, which is A. Okay, so A is kind of pointing up and to the right. I've got my fingers of my right hand pointing that way. By the way, I don't want to use my left hand because that's going to give me the exact wrong answer every single time. Okay, step 2. Curl your fingers in the direction of vector B. So I'm going to curl those same fingers this way in the direction of vector B. And now notice my thumb is pointing in the direction of the cross product. So in this case, vector C is going into the page. That's what I determined from the right-hand rule. Okay, so that's the math behind cross products. And so now let's get into magnetic forces. So here's what I want you to think about. We've got, in this picture, a wire which is carrying some kind of current. So that's shown here in black. So the current I is running along the wire. Okay, this wire, which has a current running through it, is inside of a magnetic field. Okay, so for now, let's not worry about what caused the magnetic field or why this B field is there in the first place. Let's just stipulate that there is a magnetic field here and it's uniform. Okay, so uniform just meaning it's the same everywhere. Okay, just as strong everywhere, pointing in the same direction, no matter which way, no matter which point we look at. Okay. All right. So if you do some experiments with this sort of setup, you're going to find a couple different really important results. And the first is this: if the current is parallel to the B field, so there's 0 degrees between them, then there's no force. So in other words, if I take my wire and I point it straight to the right, so the current is just running straight to the right like this, well, the angle between, again, my current and my magnetic field is going to be 0. Experimentally, there's no force on this wire if I orient it this way. Okay? Now, on the other hand, if I have my current perpendicular to B, let's say I run the wire going straight up with the current going straight up like this, then the force is at a maximum. There's actually a really large force in this case. All right? So I'm saying there's a force on this current-carrying wire. What direction is that in? Well, turns out if you want to get the direction right, it's perpendicular to both B and the current. Okay? So the direction of the force is perpendicular to both the magnetic field and the current itself. And you might be thinking, that should involve a cross product if I want to fully explain it, and that's true, so we'll get to that in a second. But the magnitude of this force is given by this. The force is proportional to the following. So the magnitude of the current, so the more current that's flowing in the wire, the greater the force that it's going to feel. Also L, the length of the wire, so the longer this wire is, the more force it's going to feel. B, so the strength of the magnetic field, if that's greater, then we're going to have more force. That makes a lot of sense. And then as it turns out, it's the sine of the angle that also matters. Okay? So if you put this all together, the force is proportional to I times L times B times sine of theta. And again, everything I said here, just take this to be an experimental result. This is just how it works when you put a wire, which has a current, inside of the magnetic field. It feels a force, and the force depends on a number of different factors. Okay. So the most sort of compact way to write the force that a current-carrying wire in a magnetic field actually feels is this. The force is equal to I L cross B. Okay, well, I is the current, B is the magnetic field, L, it's weird to think of that as a vector because we just said a second ago it's the length of the wire, but the direction of L if we think of it as a vector, it's just whichever way the current is going. Okay, so when we think about L as a vector, it's just pointing whichever way the current is going. So we've got a nice cross product here, IL cross B. And like any other cross product, we can think about the magnitude of the cross product and the direction of the cross product. So the magnitude of the force, well, that's going to be ILB sine theta, where theta is the angle between the current and my B field. If I want to know which direction this wire is going to feel a force in, then I'm going to have to use the right-hand rule because that's how cross products work. Okay, so at this point, we've talked about magnetic fields, but we haven't quite said how we measure them. We haven't talked about the units that we measure the strength of a magnetic field using. So let's get to that now. So it turns out the SI unit of magnetic field is called a Tesla, given by capital T, and this unit is defined in the following way, okay? So experimentally we know that the force is proportional to I, L, B, and sine theta. So whenever you have a proportionality, like one quantity is proportional to some other quantity, we know there's always a constant of proportionality involved in that. So the Tesla is actually defined in a clever way so that the constant of proportionality here is exactly equal to 1. So we don't need to actually state that there's a constant out front, it's just 1. Okay, now, let's think about the Tesla in the context of other units we know. Well, a Tesla is this. It's a Newton divided by an ampere divided by a meter. And that makes sense because actually if you take this equation here, you can rearrange it to say that the magnetic field is the force divided by the current times the length. So we know it's going to be some kind of force divided by a current times a length if you analyze the units. And so in the SI system we have a Newton for the force, an ampere for the current, and a meter for the length. So that's a Tesla. So it turns out a Tesla is actually a really big amount of magnetic field. If you have a magnetic field with a strength of 1 Tesla, that is very, very hard to achieve, and it's not really something you're going to find out there in the real world very often. So there's another common unit for magnetic fields called the Gauss. And the Gauss is defined this way. 1G is equal to 10 to the minus 4 T. So 1 Gauss is 10 to the minus 4 Tesla. It's a much smaller unit. And just for reference, how strong is the Earth's magnetic field? Well, it kind of depends on where you are. It's not really the same strength everywhere, but on average, it's about half a Gauss. 0.5 Gauss is the strength of Earth's magnetic field, typically. And if we put that in Tesla, that's about 5 times 10 to the minus 5 Tesla. So that gives you a sense of how a Tesla is a really big amount of magnetic field, because the Earth's magnetic field is not even close to a Tesla. All right? So moving forward, I've got a question for the class. And basically, I've thrown a lot of information at you up until this point. I want to sort of take a step back, give us a little bit of practice using the equation we just developed for the force that a wire in a magnetic field feels. Okay? So here we have a rectangular loop of wire that lies in the plane of the page, and there's a current running through that which is going clockwise. All right? So the current is just shown with these black arrows here. That's the current. Okay? Now there's a uniform magnetic field which is pointing to the right, so that's shown with the red arrows and labeled as B, that's our magnetic field. And what I want you to think about is, for each one of these segments of wire, 1, 2, 3, and 4, determine whether the force is going to be 0. Okay? If it's not 0, then figure out which direction the force is in. Okay, so 2 steps. For each one of these wires, try to see if it's experiencing 0 force or non-zero force. And then if the answer is there is a force, it's not 0, then figure out which direction it's going in. Okay, so pause the video, try to work this out, and then we'll come back to it. Okay, so here is how we work this one out. So just to copy down the diagram we had earlier, I have this rectangular loop of wire, just like this, and the current is running through it in a direction clockwise. And we said that this is going to be segment 1, this is going to be segment 2, this is segment 3, and this is segment 4. At the same time, we have a magnetic field. So I'll draw the magnetic field lines going to the right. And that's what we're dealing with. Okay, so for each one of these segments of wire, we have the force is equal to I times L cross B. So the force is given by a cross product, and that means we can break it into two pieces. We can say there is a direction to this force, which is given by the right-hand rule. There's also a magnitude for this force. And, well, this is how it works whenever we have a cross product. Remember, you take I is just a constant out front, take the magnitude of the first vector, times the magnitude of the second vector, times sine of the angle between them. So let's just note that theta is what? It's the angle between the B field and the current. Okay? So basically we're going to go through this whole process for each one of these numbered segments of wire. Okay, let's start with segment number 1, right here. Maybe the first thing we should do is establish what the angle between the current and the B field is. Well, in this case, that's really easy. The B field is going straight to the right, and at least for this top portion of the loop, the current is going straight to the right, which means there is 0 degrees between them. There's no angle there. And that automatically implies that the magnitude of the force here is equal to 0, because if I take sine of 0, I'm going to get 0. There's no force there. Okay, so that's all we had to do. We just had to say the force is 0. Okay, so for number 2, let's think about that angle again. Now the current in this case is running down, and the B field is still just going to the right. So in this case, we actually have a 90-degree angle between them. So we can't say the force is 0, because actually, when I take sine of 90, I get the biggest possible force, because sine of 90 is 1, and that's the maximum value that sine can have. So, okay, in this case, I don't want to say the force is 0. Instead, what I want to do is use the right-hand rule to determine which way the force is going. So remember how this works. I have I times L cross B. So I'm taking a cross product. The right-hand rule says I take the fingers of my right hand, put them in the direction of the first vector, which is L, and then curl my fingers in the direction of the second vector, which is B. Okay, so this is a little tricky to do. I might have to turn the paper kind of sideways to do it. Okay, so I'm looking at segment number 2. So my first vector, L, is just going with the current. And then my second vector, B, is going with the B field, so I have to curl this way. And now my thumb is pointing up. Okay? So F2 is out of the page. And so how do I show that F2 is out of the page? On the diagram, what I would do is put a little symbol like this. Okay? So normally, when we draw a vector on a diagram, you see it as an arrow pointing a certain way. But what if your vector is coming out of the page like this? Well, the way you show that is with this little dot surrounded by a circle, and this is to bring to mind an arrow coming at you. Okay? So this is F2. It's coming out of the page. And then let's just say up here F1 is 0. Okay, now let's go to segment number 3. Well, what's going on with this one? The current is running to the left, and the B field is still going to the right. So the angle between them is 180. But sine of 180 is also 0. So we automatically know that F3 is equal to 0. So let's write that down here. F3 is equal to 0. And then the last one to do is segment number 4. Again, let's think about the angle. In this case, the current is going straight up, and the B field is going straight to the right. So the angle between them is 90, once again, so we can't say the force is 0. But what we can do is figure out the direction of the force using the right-hand rule. So this works just like before. I've got to take my right hand, and I have to start by taking the fingers of my right hand and pointing them in the direction of the current, which is this way. Then I have to curl them in the direction of the B field, which is this way. This is kind of hard to see, guys, but hopefully you can follow along. If you do this, my thumb is going to be pointing into the page. So F4 is into the page. How do I show on a diagram that I have a vector going into the page? Well, this is the symbol. It's a little X with a circle around it. Again, in this case, think of it as an arrow traveling away from you. That's what that's meant to represent. Okay, last thing to note here is what happens if I have a force on one side of an object that's pointing one way, and a force on the other side of the object that's pointing the opposite direction. So here, let's take this pencil for instance. Okay, if I push down on this end, and then I push up on this end, what happens to the pencil? It starts to rotate. So apparently, that's what's happening here. This coil that's carrying this wire in this magnetic field is feeling a force this way, it's coming out of the page, so it's like you're pulling this side up out of the page, while at the same time, you're pushing this side down into the page. That's going to make it rotate. That's going to make it spin. And that's the actual basic principle behind an electric motor. Okay? So that's just a preview. We're going to talk more about electric motors later on, but you can kind of get a general sense of how they work just based on this. Okay, so let's do some more practice. So this is kind of an interesting example of how a wire that's carrying a current, if it's in a magnetic field, is going to feel a force. Well, I mean, think about the power lines that you see outside every day. Okay? They're carrying currents, and also they're inside a magnetic field. They're inside of Earth's magnetic field. So there's going to be some kind of force due to Earth's magnetic field that these power lines actually feel. Let's try to figure out how much that force would be. Okay, so we have to put some numbers on this. Let's start by saying that the power line is 50 meters long, and the current that's running through the power line is 1,350 amps. Okay? We're going to say that the Earth's magnetic field has a magnitude of 4.5 times 10 to the minus 5 Tesla, and let's just say it's pointing straight north. What is the magnitude and direction of the force on the power line if the current is going east, if the current's going west, and then if the current is going south? Okay, let's work this out. So this is really just another application of F equals IL cross B. Same basic formula, but this time we're actually going to make some calculations with it. So we have three parts to this. Let's start with if the current is flowing due east. Okay, so here let's actually draw some directions like this. So east on our diagram is going to be to the right. Okay, north is going to be pointing up. And okay, so this is what it looks like if we have sort of a bird's eye view of the map, right? This is the direction going north. This is the direction going east. Now, if I'm going up, okay, like off the ground, well, that would be out of the page. So up is out of the page. And then, of course, if I'm going down, then I'd be going into the page. Okay, so up towards the sky is out of the page. Down into the ground is into the page. That's how we set up our directions. And then let's draw the magnetic field. Well, we just have
a field pointing like this, straight north. That's Earth's magnetic field. And there's B. Okay, and then inside of that magnetic field, we're imagining that there's a power line which is carrying a current, in this case going east. So that's the situation. Magnetic field line's going north, the current's going east. Well, look, I already know the angle between these two. It's a 90-degree angle. So I know there's going to be some kind of force. And if I want to get a sense of what the direction of the force is, using IL cross B, well, the direction is going to be given by the right-hand rule. So remember how this works. I take the fingers of my right hand and I point them in the direction of the current, which is this, and then I curl them in the direction of the B field like this. Now my thumb's pointing straight up. So it looks like the direction is upwards. Okay? It's out of the page. Okay, so quite literally, this power line is going to be pulled up with some kind of force. But let's figure out how strong that force is. So we have F equals ILB sine theta. That's how I get the magnitude of the force. And this is sort of just a plug and chug. What we have is the current. It's going to be 1350 amps. The length is going to be 50 meters. That's how long the wire is. The magnetic field, 4.5 10 to the minus 5 Tesla. And, okay, let's use our unit equivalency here. A Tesla, as we said before, is a Newton divided by an amp times a meter. And then we take sine of the angle, which is in this case 90, right? The current and the B field are at 90 degrees. Okay, so if you do the calculation, you're going to get something kind of small, 3.04, and the units here are newtons. So that's how much force the wire is going to feel, and it's going to be going upwards. Okay, let's do the next one. The current is flowing due west. Okay, so it's pretty much the same exact picture we already had. I'm not going to redraw it, except now the current is going due west, which is to the left in our picture. So actually, as far as the force goes, the magnitude is exactly the same, because we still have the same amount of current, the same length of wire, the same strength of the magnetic field, and there's still a 90-degree angle between the current and the magnetic field. It's just the current's now going west instead of east. So the magnitude of the force is exactly the same as before. So 3.04 newtons. Now as far as the direction, now we have to do the right-hand rule. Okay, the direction is given by the right-hand rule. So now I'm imagining the current is going west. So I have to take the fingers of my right hand and point them west. And then I have to curl them in the direction of B. So I have to curl them up. Okay, so the way I'm holding my hand right now, this is not going to work. I can't curl my fingers up in the direction of B. I have to flip my hand over like this, and then I can do this. So then I can take fingers in the direction of the current, curl in the direction of B. Now my thumb is going downwards or into the page. So in this case, my power line is being pulled down with this much force, but same amount of force as before. Okay, the last question here is if the current is flowing due south. Okay, now let's think about, in this case, what our angle would be. So if I have my B field pointing straight north, and then I have my current going straight south, the angle between those two is 180. And we've already seen that if there's a 180-degree angle between two vectors, the cross product is going to be 0. So there's no force in that case. 0 force. So that's how that works. And we'll do a couple more. So this is kind of a weird example, but kind of gets you thinking about magnetic forces. We have a circuit shown right here, which is really simple. It's just a 12-volt battery connected to a 1.65 ohm resistor. You also have a magnetic field, which is shown right here. And the magnetic field is coming out of the page. So we have a uniform magnetic field in this little region here in the box that's coming out of the page. The magnetic field only exists in this box. So as soon as we go outside that box, the magnetic field goes to 0. It's totally confined to this box right here. Okay? So that means only part of the circuit here is in the magnetic field. Only this bottom part of the circuit is in the magnetic field. Okay? And so I want you to think of this as being vertical. So in other words, there is a magnetic force acting on this circuit, which is pushing it up. But of course, there's a force of gravity pulling it down. And we're going to imagine that these two forces are perfectly balanced out so that our circuit is levitated. It's just floating there in the magnetic field. It's just suspended in air. So based on all of this, okay, let's figure out the mass of the circuit. So we're going to figure out the mass of the circuit. And so here's how that goes. So, I mean, the first thing to note is, how does current flow in the circuit? We need to get the direction of the current right, because as we've seen, the direction of the force is determined by the direction of the current. So we need to get this straight. This is our circuit. We have a voltage source, battery, negative, positive terminal, and a resistor. We know how current flows. Conventional current flows off of the positive terminal of a battery, goes all the way around the circuit, back into the negative terminal. So that's I. Current is flowing clockwise in this case. Okay, we'd also like to know how much current is flowing, because that also matters. And we're going to just use Ohm's law. V is equal to IR. The voltage of the battery is equal to the current flowing through the circuit times this resistance. And so that gives us I is equal to V divided by R. The current we're looking for is the voltage divided by the resistance. And actually, let's not even put in values just quite yet. Let's just leave it at that. So the current is the voltage divided by the resistance, and the current is going clockwise. Okay, so the next thing we're going to do is we're going to find the magnetic force on each segment. So basically the circuit is rectangular in its shape, and we're going to find the magnetic force on each segment of wire. So here's what we have. Let's call this segment 1 on the top. Okay, let's call this segment 2 on the right side. Let's call this segment 3 on the bottom. And then segment 4 on the left side. And what I'm going to do is show that only part of the circuit is actually in the magnetic field by drawing this little line. So B is equal to 0 on top of that line. But below the line, B is equal to 1.45 Tesla, and it's pointing out of the page. Okay, well, we know how this magnetic force works by now. It's given by IL cross B. And so we're just going to analyze each segment of the circuit to figure out what the force is. Okay? So here, let's start with segment number 1. Well, segment number 1 is not even inside of the B field, so the force on segment number 1 is 0. Okay, not in B field. The force on segment number 2, let's think about what direction it's in to start off, okay? So, sort of reorient the picture. Okay, if I take my fingers in the direction of the current, like this, and then I curl the fingers of my right hand in the direction of the field, which is coming out of the page. So I have to take the fingers of my right hand, they're pointing in the direction of the current. In order to curl them out of the page like this is what I have to do. And it looks like my thumb is now pointing to the left. So the force on segment number 2 is pointing to the left by the right hand rule. All right, actually now I'm going to skip to segment number 4 because this is going to be useful. Segment number 4, if I take the fingers of my right hand, point them in the direction of that current, so my fingers are pointing up like this, then I have to curl my fingers out of the page like this. Now my thumb is pointing to the right, so that would be the force on segment number 4. So here's the thing about F2 and F4. One is pointing to the left, and the other is pointing to the right. And we show that they have the same exact amount of force acting on them, because after all, we have the same strength of magnetic field, we have the same length of wire, we have the same current running through 2 and 4. So these just cancel out. So the force pointing to the left, acting on wire 2, and the force pointing to the right, acting on wire 4, are going to cancel out. So the only thing that is left is number 3. Okay, so let's figure out what direction this is. Okay, so by the right hand rule, if I take the fingers of my right hand, point them in the direction of the current like this, I'd have to curl out of the page for the direction of the B field. Now my thumb is pointing up. So F3 is up, and that's exactly why this thing can float in the magnetic field, because we have a magnetic force going up and a gravitational force pulling it down, and those balance out and it just floats there. That's the idea. So how much force? Well, the magnitude of a magnetic force on a wire is ILB sine of theta. And actually here, let's just think about what is the angle theta in this case. So my current is going again to the right, or sorry, to the left, and then my B field is coming out of the page like this. Well, that's a 90-degree angle, right? If I have something going on the plane of the page to the left and a B field coming out of the page, they make a 90-degree angle with respect to each other. And sine of 90 is just 1, so I can just write this as ILB. But wait, over here, I said the current is V over R, so let's bring that result down here. I have V divided by R times LB. That is going to be the force from the magnetic field. Okay. So now what can we do with this? We can put a number to it. How much force is the magnetic field exerting on this loop of wire? Well, so it looks like on top I have V, which is 12 volts. I have L, which in the picture was 12.5 centimeters, or 0.125 meters. And then the B field was, what was it? 1.45 Tesla. And the last thing we're going to do is divide by the resistance, which is 1.65 ohms. I don't want to get into the unit analysis right now, but basically everything is in SI units going into the calculation. What should come out of that calculation is the SI unit of newtons. And if you do the calculation, you get 1.318 newtons. Okay. Now, we said just a second ago that if the circuit is floating, then we must have a balance of two forces. The magnetic force, which we just calculated, and gravity, which is pulling it down. Okay, so the force pushing it up and pulling it down equal each other in terms of magnitude, and what we get is something that's just floating there. Okay, so what is the force of gravity? Well, it's m times g. And in this case, we're trying to figure out m. We want to know the mass. So we take the magnetic force, divide out g, which is 1.318 newtons divided by 9.8 meters per second squared, and that gives us 0.1344, let's keep 3 sig figs here, kilograms, or if we want to convert this to grams, about 134 grams. So again, this is kind of just a toy example. This is the most roundabout way in the world that you could weigh something, but it works, right? We know that the magnetic force balances out gravity, so we can actually work our way to what the mass of this circuit is. Okay, so now we're going to do a calculus-based example. So this is going to be a little bit tricky, but this is something you should know how to do. And this example says we have a semicircular loop of wire with a radius, which we'll just call r. So the radius r is right here. And this wire is carrying a current, which we'll call I. Okay? Now this half of a circle, this loop, is inside of a uniform magnetic field, B, which is perpendicular to the semicircle. So in this case, imagine the B field lines are going in to the page, and it's completely uniform. All right, we're going to do two things. Find the direction of the magnetic force acting on the wire, and then we're going to find an expression for the magnitude of the magnetic force acting on the wire in terms of all of these variables, which, again, we're not going to plug in numbers for. Okay, so that's the idea. We have a half circle of wire carrying a current like this. That half circle is inside of the magnetic field shown here. Okay, so let's work it out. Now, the first question here is about the direction. So I want to sort of convince you that from symmetry, we can argue that the x component of the force acting on this loop of wire is equal to 0. So let's spell out exactly why that's the case. All right, so here is our coordinate system, x, y, like so. And then here is our half circle, which carries a current going this way. And of course, this whole thing is inside of a magnetic field, which is going into the page. So that's the idea. The current is going along the wire, and then the magnetic field is going into the page. Now, we have the idea that F is equal to I L cross B. In this case, I want us to write this in differential form. So what does that mean? dF some tiny little infinitesimal amount of force is equal to I times dl, which is some tiny infinitesimal amount of length along this wire, cross b. So in other words, I'm kind of turning this into a calculus problem where I take the wire and break it into infinitesimal little bits and see how those little forces add together. Okay, so how about we start with something on this side of the loop. Let's have this be our DL. And let's actually call it DL1. And remember how these DL vectors work? They just point whichever way the current is going. Okay, now, on the exact opposite side of the wire here, I want us to think of another little piece of the overall wire, which I'll call DL2. And it's a vector pointing in this direction, just the direction the current is flowing in at that point. And what I want to get a sense of is, what is the force acting on this little segment, and what is the force acting on that little segment? And the way we're going to figure it out is using the right-hand rule. Because this says I need to take a cross product of DL and B. Well, with this one, that means I'm going to point my fingers in the direction of DL, and I'm going to curl them in the direction of B, which gives me this situation. Okay? The force is pointing out, away from the center of the circle like this. Now, what if I'm over here, talking about this segment? Well, similar thing, DL cross B. Point the fingers of your right hand in the direction of your DL. Curl them in the direction of your B field, which is into the page. And now your thumb is pointing in the direction of the force, which, just like before, is going to be pointing away from the center of the circle, like this. Now, one thing you'll notice about DF1 and DF2 is that it's totally symmetric. It's the same amount of force, whether I'm here or here. But the x components are going to cancel out. Right? So notice how the x components are going in opposite directions, but the y components are going in the same direction. So let's actually show that explicitly, okay? If I take df1 and then I add it to df2, these two vectors add in such a way, so I'm actually showing them tip to tail. These vectors add in such a way that the total force is just going up, okay? So the x components cancel out. The force is only in the y direction. So from symmetry, that's what we could figure out, is that the force is only going in the y direction. Okay, so that answers the first part of the question, which is, what direction is the force? It's in the y direction. Now, let's get an expression for that force. So now we'll find Fy, knowing that Fx is going to be 0. So I'm going to have to redraw this picture a little bit. We have a half circle like this. And we're breaking that circle up into little pieces. And I'll draw one of those pieces right here. This will be my DL. And so there's some angles we need to know about in this diagram. The first one is, let's call this right here phi. And of course the radius of the circle is r. But what's phi telling me? Well, phi basically locates where my DL is located. So for instance, if phi were 0, then I'd be talking about this DL. And if phi were pi over 2, I'd be talking about this DL. And if phi were equal to pi, I'd be talking about this DL. Just locates which one. But also notice how the DL itself it spans a certain angle. So here let's write segment DL spans angle d phi. And d phi is shown right there. Okay? So now let's show our force vector dF, which from previous work is just pointing sort of up and to the right like this. There's my dF. And this dF vector can be broken into components. Probably the easiest way is just to draw a little triangle right here where this is dF x and this is dF y, and then this angle is phi from down here. It's the same phi. Now this is useful because I actually don't have to worry about dfx at all, because I know the x components are going to cancel and I'm just going to get 0. So I'm only going to focus my attention for the time being on dfy. Well, dfy is equal to the magnitude of df times sine of my angle phi, where this is my angle phi, down here. Okay? All right. Well, how does the magnitude of df actually work? Well, let's just copy down once again that df is equal to I dl crossed with b. And so the magnitude of this vector, just like the magnitude of any cross product that you ever do, is equal to I times the magnitude of dl times the magnitude of b, and then times the sine of the angle between them. Now let's actually think about what is the angle between dl and b. Well, b is always going into the page, and then dl is always in the plane of the page, right? So it kind of loops around here, but there's actually always a 90-degree angle between my current, which is again in the plane of the page, so might be pointing straight up over here, and then straight to the right over here, and then straight down here. But my B field is always out of the page. So there's always a 90-degree angle between my current and my B field. Okay? Let's get a handle on one other thing, which is that DL, this is what we call an arc length, right? It's a section of a circle, a small section of a circle. And the way arc lengths work is, if you take the radius times the angle spanned, so r times d phi, you get the arc length. So that's all we're applying here, is the idea that dl is an arc length. Okay, so this is kind of a lot. Let's put it all together. So what do we have? The magnitude, or let's write dfy, is equal to the magnitude of df. So let's plug in for that. I times dl times b, and then sine theta is sine 90, which is 1. So that's my df magnitude. But then I have sine of phi from over here. And then let's plug in the fact that from before, we could say that dl is going to be r d phi. So plug that in for dl. And then we have b sine of phi. Okay, so to clean this up a little bit, what we have is I times r times b. Those are all constants. And then we have sine of phi times d phi. Okay, so if I want to get the overall force in the y direction, what I have to do is integrate over all my dfy's. If I add up all of these tiny little bits of force that each segment gets, and I include the whole loop, then I'll get the overall force. This is an integral. Now in this integral, what I'm plugging in is I r times b sine phi d phi. But I have some constants I can immediately pull out, which are the current, which is I, the radius, which is R, and then the strength of the magnetic field, which is B. All of these things are constant. So IRB comes out, and then all we have is sine phi d phi inside of the integral left over. Question is, what are the limits? Well, phi starts over here at 0, and then if we trace it all the way around to the half circle, we get pi. So 0 to pi, sine phi d phi is what we have to integrate. Well, the integral of the sine function is just, what is it, minus cosine? Okay. And so I have minus cosine evaluated from 0 to pi. And let's plug in those limits. So I have a negative sign out front from here, IRB, then I have cosine of pi minus cosine of 0, which means I have minus IRB. Cosine of pi is negative 1. Cosine of 0 is 1. So I have negative 2 in the brackets. Minus IRB times negative 2, or simply 2 IRB. Okay, so the force is 2 times IRB in the positive y direction. So if you put half of a circle carrying a current in a magnetic field that's pointing into the page, that's the force that it's going to feel. 2 times IRB in the y direction. Okay. So we did a ton of different examples on how to find a magnetic force, okay, for a current carrying wire which is in a magnetic field. So all the different examples we've gone over are just some variation of this. Okay? So the next thing is, let's talk about magnetic forces on moving charges. So in other words, instead of saying we're going to put a wire which is carrying some current into a magnetic field and then talk about what the force acting on that is, let's instead put a single moving charge, maybe like a single electron, a single proton, whatever the case may be, in a magnetic field and try to understand what force acts on it. Okay, so we're kind of doing this in reverse. We already know how to describe the force on a segment of wire that's in a magnetic field. Okay, this is an experimental result. We can actually use that to figure out what is the force on individual moving point charges in this wire. So remember this sort of microscopic view of current in a wire. We have a bunch of moving charges, and they all flow in a certain direction, which is given by what we call the drift velocity, but let's just say they're all going to the right in this case. Okay, so the force on the overall wire segment is IL cross B, as we've seen. And we're going to try to take what we know about that to say something about the individual charges. So let's say each individual moving charge is Q, so that's the electric charge. And then the velocity, let's call that V. Okay? All right, now what I want us to think about is we have a shaded surface right here that charge is moving through. Okay? So I want to think about, in some amount of time, let's call it delta t, let's just say that n particles move through there. We're not going to assign numbers to that, but it could be, for instance, 1 billion particles move through the shaded surface in 1 second, right? That would be n in delta t. For now, let's just leave that symbolic. What's the current going to be given by? Well, the current is defined as the amount of charge in total flowing through this surface divided by the time interval it takes for that charge to go through the surface. In other words, delta Q over delta T is the current flowing through this surface. Now delta Q, think about that as being the total amount of charge. I can think about that total amount of charge as being n times little q. Okay, so if I take the total number of charges I have times the charge each one gets, that gives me the total charge going through the surface. Okay, so that's a good expression for the current that we're going to use. The next thing we can think about is L. Because, well, actually here, let's just go back 1 second. So what I'm eventually going to do with this is I'm going to take this expression for the current and put it in right here to the formula that we already have developed. And I'm going to do something similar for L, okay, the length of the wire. I'm going to come up with some expression for that we can sub into this. Okay, so the length L that we're talking about in this case, think about that as the distance that charges move in time delta t after they move through that surface. Okay, well, this is pretty easy because if we take the product of velocity in delta t, so if you take a velocity times a time, you get that distance traveled, and then L being a vector just means it's going to be pointing to the right in the direction of the current, or in the direction that charges are moving. Okay, so if we take, again, the velocity times the time, we get the distance that the charges travel, and that's vector L. So now, let's make all those substitutions that I talked about. The current can be thought of as n times little q, so the number of charges times the charge each one has, divided by delta t, times the velocity of the charges times delta t, that's what I subbed in for L, cross that with B, and we get the force. Well, the reason this is going to simplify things is, for one, delta t drops out. That goes away altogether. And then the force is N times Q V cross B, after we cancel out the delta t. Now, to be clear, what is this force? This is the amount of force that all of the different charges together are feeling. Okay? In other words, this is the force for n different charges. If I want the force on one charge, all I would do is divide out my n. Okay? Because that would be the force that an individual charge actually gets. So the force on one of these particles is QV cross B. And this is a really important result. This is the magnetic force on a moving point charge. It's given by QV cross B. Okay, so now we know that an individual point charge moving through a magnetic field in some way is going to have a force acting on it, which is equal to QV cross B. And again, we're dealing with a cross product, so we have to think about how we calculate a cross product in terms of magnitude and in terms of direction. Okay, well, the direction, as always, for a cross product is going to be given by the right-hand rule, whereas the magnitude of the force is given by this. Okay, we take Q times the magnitude of V times the magnitude of B times sine of theta, where the following are the variables here. We have Q, that's the magnitude of the charge. V is the speed of the charge, how fast it's going. B is the magnitude of the B field, or the strength of the B field. And then theta is the angle between the velocity vector and the B field. Okay? So, how do we deal with the fact then that we have sometimes positive charges and negative charges? So for instance, I could have a proton moving in a magnetic field or an electron moving in a magnetic field, and those would be different situations. So, if I have the same velocity in the same B field for two different particles, okay, and one of those particles is positive, the other particle is negative, that's what I'm showing you here, because they're both same velocity, both going to the right. They're in the same B field, which is going into the page in this figure. But the force is going to be different because one is positive and the other is negative. So let me show you how that works. Okay? So let's take this one, the positive charge, to start. If I want to know what the direction of the force is, well, I'm going to take my right hand, and I'm going to take my fingers and point them in the direction of V. Then I'm going to curl those fingers in the direction of the B field, which is into the page. And now look what's happening. My thumb is pointing up. So the force on this positive charge is going to be up. What happens with this negative charge? Well, we'll do V crossed with B, but because the charge carries a negative sign, that actually flips the direction of the force. So now it's going down. So everything else being the same velocity, the same magnetic field, positive and negative charges feel opposite forces. Okay? Positive charge will feel a force going one way, a negative charge is going to feel a force going the other way. That's what we just found out. And so with that said, we're going to do some examples where we have a little bit of practice thinking about this magnetic force and how it comes out. So we have a uniform magnetic field going to the right. For each particle shown below, determine whether the magnetic force is zero. If the force is not zero, then we'll find the direction of the force. Okay, so before we go into each individual example, we have 4 of them. Let me just remind you how we're going to think about this. Okay, the magnetic force on a moving point charge is given by F equals QV crossed with B. Okay, the magnitude. Okay, that's going to be QVB sine of theta. And actually, let's just really quick think about under what circumstances would the force go to 0? Well, if theta is equal to 0, or if it's equal to 180, because sine of 0 gives you 0, and then sine of 180 also gives you 0. In both cases, we're going to have 0 force. So what does that mean? If my velocity is going exactly with the B field lines, or exactly against it, either way, there's no force. Okay, and then finally, if we want to understand the direction, then we're just using the right-hand rule. So I think that's enough to really just have in your head to work out each one of the examples. So let's go back to the examples. Okay, so let's start with charge A. And the way to read this diagram here is anything that's shown in blue, that will be a positive charge, and anything shown in red, that will be a negative charge. My B field lines are shown in green, they're going to the right. It's a uniform magnetic field going to the right. Okay, so let's start with charge A. First, is the force on charge A going to be 0? Well, I think the answer is no, obviously, because the only way when we have 0 force is if the velocity is going at 0 degrees or 180 degrees to the B field lines, but in this case, the velocity is at 90 degrees to the B field lines, so it's not going to be 0 force. Okay, let's find the direction of the force in that case. Well, if I want to find the direction of the force, I use the right-hand rule, where I start by putting the fingers of my right hand in the direction of velocity, and then I take the same fingers that are going down and curl them in the direction of the B field. So what's the answer here? For charge A, the force is coming out of the page. For charge A, the force is coming out of the page towards you. So we can call that the positive z direction out of the page. All right, let's go to charge B. That's this one. Now my velocity vector is kind of going up and to the right. And again, I don't think I have 0 force here because my velocity is not going exactly with or exactly against the B field lines. So I have to figure out what direction it is now. Okay, so I'll take my fingers and I'll point them in the direction of the velocity, and then I'll curl them in the direction of the B field, and now my thumb is going into the page. But here's the thing, this is a negative charge. If it were a positive charge, the force would be going into the page, but since it's negative, I have to flip that around, the force is actually going out of the page. So for both A and B, the force is going out of the page or in the positive z direction. Okay, so A and B, it's the same answer. The force is out of the page or the positive z direction. Okay, let's look at charge C next. Now, charge C, there's no velocity vector drawn next to it, which is implying that charge C is not moving. Okay? Well, this is pretty simple because if you take QV cross B and you have zero velocity, you're automatically going to get zero force. So that's important to remember. If you have a charge that is not moving, it doesn't feel a magnetic force. It's only moving charges that feel a magnetic force. So the answer for charge C is 0. All right, then we'll go to charge D. What's going on here? Well, in this case, my velocity is exactly to the right, and it's exactly lined up with my B field lines. So that means we have no force. The angle between the velocity and B is 0 degrees. As we said, that means there is zero force. Okay, so to recap, A and B, they're both experiencing a force which is coming out of the page, and then C and D are both experiencing zero force. Okay, let's do one more example, just to make sure we have these ideas straight, and then that'll be it for today. In this example, we're really doing the same thing. We're going to figure out what the direction of the magnetic force is, but as you'll see in this case, it's a little bit more complicated. What we're going to have to do is give an angle, which tells us which way the force is going. So it says give each direction as an angle off the positive x-axis going counterclockwise. Right? So to set this up, first note that the B field isn't the same as before in the previous example. Now the B field is coming out of the page. So imagine these lines are coming out at you, out of the page. And then we have a bunch of different charges, A, B, C, and D, moving in the plane of the page. Okay? So for each one of these, we're going to figure out what direction the force is. Okay, so let's work this out. How about we start with charge A? And actually, all this information I wrote down is still useful, right? Because we can think about the magnetic force in terms of QV cross B, and the direction is going to be given by the right-hand rule. So let's take charge A. And in this case, I'm just going to copy down everything we know. It was a positive charge. It was moving down, so its velocity is like this. And it's in a B field, which is coming out of the page. So again, that's how you draw a vector coming out of the page. All we have to do is the right-hand rule to determine the direction. Okay, so here, let's apply the right-hand rule to this case. All right, so it's fingers of your right hand. Here, let me turn it sideways. Fingers of your right hand in the direction of V. Curl those fingers out of the page in the direction of B, and your thumb is pointing in the direction of the force. So your thumb should be pointing in the diagram straight to the left. So if I were to talk about the direction of that force as an angle from the positive x-axis, which is this the dashed line right here, that'd be, let's call that theta A. Theta A is 180. Okay, because the force is pointing in the negative x direction, the angle is 180. All right, so moving on, charge B. What's going on with charge B? Well, charge B, for one, is negative, so that's an important difference. Its velocity is going to the right, but it's in the same magnetic field, so that's coming out of the page. So if we do the right-hand rule to this one, if we do, okay, V point your fingers in the direction of V, curl them in the direction of B, that's coming out of the page like this. Your thumb's going to be pointing down, like this, in the negative Y direction. But it's a negative charge, so you have to flip that, it's going up. So to reiterate, a positive charge would feel a force going this way. This negative charge feels a force going the other way. So the force is going up. And if I want the angle that that force makes with the positive x-axis, that'd be theta b here. Well, theta b is just 90 degrees. Okay, so that's how it works. If we move on to charge C, now here's what's going on. Charge C, for one, is a positive charge, and it's moving at this angle, which is 23 degrees with respect to the positive x-axis, and it's in the same exact B field, which is coming out of the page, same as before. Okay, let's figure out what direction the force is going to be in. And before we get into the right-hand rule, just remember the force is going to be perpendicular to both V and B. That's how a cross product works. If the force is given by QV cross B, the force has to be perpendicular to both of these two vectors. And basically that gives us two options. Okay, it can be pointing kind of down and to the left like this, because it'll be perpendicular to V, and of course it's perpendicular to B, which is just coming out of the page. Or it can be, down and to the right like this, or up and to the left like this. Those are our two options. Okay? And all the right-hand rule is doing is helping us figure out which one of those is the correct option. So the right-hand rule says we take our right hand, fingers in the direction of V, curl those fingers up out of the page in the direction of B. It looks like my thumb is now pointing down and to the right, which was this, this direction right here. Now, how do I know what the angle is? Well, first, let me indicate this angle right here. So below the x-axis, I have to go a certain number of degrees. Let's call this alpha. How about? Well, the 23-degree angle and alpha, if I add them together, that's going to be 90, because I know that the velocity and the force have to be at a right angle to one another. So alpha is just nothing more than 90 minus 23, or 67 degrees. Okay? Now that's not exactly the angle I'm looking for. The angle I'm looking for is this one. So go off the positive x-axis, go counterclockwise until you get to the force. Let's just call this theta c right here. And it looks like if I want theta c, that's just 360 minus alpha, because of course if I add the two angles, theta c and alpha together, I get a full circle. So I have 360 minus 67, which is 293 degrees. Okay? So that's the angle that this force makes with the positive x-axis. All right, let's do one more. Charge D. So in this case, here's what we were given. We have a negative charge. It's moving like this, kind of in the second quadrant, where there's a 55-degree angle between the y-axis and the velocity vector. And as usual, we're in the same magnetic field pointing out of the page. So it's the same deal. We do V cross B, and it looks like my thumb is pointing kind of like this into the first quadrant, right? But I have a negative charge, which means I need to flip that, so I'm actually going down like this into the third quadrant. Let me actually draw that. So here we go. That's my force from the right-hand rule. And, okay. How do I get the angle I'm looking for, which is this one, theta d? Well, theta d, let's kind of take it in chunks. We have a 90-degree angle to get from the x-axis to the y-axis. Then we have another 55-degree angle to get to our velocity vector. But then we have another 90-degree angle to get to our force, because again, velocity and force are always going to be at 90 degrees. Add these numbers up, you get 235 degrees. That's the angle. Okay, so that was our introduction to magnetic fields and magnetic forces. When we come back for the second part of this lecture, what we're going to be talking about is applications of everything we just learned. So, for instance, we're going to learn a little bit about particle physics. How is it that in a lab you can accelerate a charge to a really, really big speed and maybe smash it into another particle to see what happens? That has a lot to do with magnetic fields and charges moving in magnetic fields. So that's next time. Until then, be safe, be healthy out there. See you in the next one.